Hi guys, this is the homework tutorial for adding and subtracting fractions worksheet B. You might notice if you're tuning in that you're lucky if you're tuning into this broadcast because these are actually the problems from the worksheet. So there being 8 problems, we're doing 3 together, and you know what, just a side note, that's 3 out of 8 problems. Of course that is 0.375, so I'm helping you basically with 37.5% of the assignment. But you know what, it's really straightforward. I didn't think you'd have that much trouble with it, and we did go over these in class today on worksheet A. So let's go ahead and start with number 2. The big thing here is this: if we're going to be adding and subtracting fractions, not just fractions but mixed numbers as well, you need to recall that we cannot put things together or take them apart mathematically, okay, unless they have the same denominator, or we can think about it as the same size pieces or the same stuff, because ninths are not the same as 27ths. So our main ambition really is this: we know how to add, we know how to subtract. It's fingers and toes. Okay, we can check it on a calculator. The big thing is this: how do you go about finding a common denominator? And the deal is this: when you look at the two denominators, what we need to be asking ourselves is, what is the least common multiple between these two denominators? Now, when I say multiple, multiples of 2, for example, would be 2, 4, 6, 8, 10, so on and so forth. How about 3? It would be 3, 6, 9, 12, 15, so on and so forth. I look at these two things and, hey, nobody wants to go through the multiples of 27 in their head. It's 27, I think, followed by 54, excuse me, followed by 81. But here's the deal. You know, you look at 9 and 27, and most of the time people can figure this out. Hey, if we took 9 times 3, we could actually transform that to be 27. Now, if it came down to a bind, and this is one thing we've been talking about in class, especially after going over the algorithm that we created, is this: we could technically take 9 times 27 and 27 times 9, and that must be a common denominator between the two. The only unfortunate thing about doing so is 2 things. 1, 9 times 27 is ginormous, and 2, we don't like to deal with big numbers. So most of the time we're looking for this least common multiple between the two denominators. Okay, in this case it is 27. So here's the deal. I might ask, how would we transform 9 into 27? Well, we may multiply or divide. And in this case we need to inflate the number. So we are going to multiply. So the question is, what can we take times 9 to get 27? Now, thinking in terms of scale factor, because that's what it is that we're using, scale factor, you might say, okay, what can I take times 9 to get 27? Well, work backwards. What is 27 divided by 9? In this case, it is 3. I do need you to remember that if you're going to take this denominator times this scale factor 3, what you do to the bottom of the denominator, you must also do to the numerator. If we do not do this, it will not maintain an equivalent fraction of what we started with. Now, I do prefer this. Please and thank you. Show your work and rewrite the problem. What I mean is, well, hey, 8 times 3 is 24, so we have 24 27ths plus another 11 27ths. I would like to see you rewrite the problem, please. Okay? So we go through this, I say, alright, well, I got 27ths and 27ths, and hey, if you're putting 27ths with 27ths, it's not a shocker to say, what are you going to have when you end up with your answer? More 27ths. The question is, how many? Okay, well, 24 plus 11. I always like adding 11 because what we can do is we can just kick up those 2 digits, 1 each one. So it'll be 3 and a 5. Now, 35 27ths. Here's the neat thing about it. You hear me ask this in class all the time. I say, is this the correct answer? And you guys all say, yes. Hey, it is correct. That is not wrong. However, I need you to recall, we cannot leave it in this form. So 2 things we need to check for, because this is an improper fraction. We need to check for, hey, do 35 and 27 share any common factors? Now, we could go about this by creating a factor tree for 27 and a factor tree for 35. And what you're going to discover is this: they don't really have any common factors. 35, its factors are 1 and 35, and 5 and 7. None of those, except for 1, go into 27, because the other factors of 27 are 3 and 9. I will say this, however: this is an improper fraction. We must discover, hey, how many wholes could we get out of this? That would be equal to how many times 27 goes into 35 completely without going over. Of course, in this instance, it would be 1 whole time. So we say 27 goes into 35 once, and we have to ask, with how many 27s left over? So if it went in 1 time, hey, 1 times 27 is 27. Let's just take that 27 off of this 35. And if you're looking at this, we do have to borrow. So we will borrow from the 3. It becomes a 2. And we say, well, what is 15 minus 7? Of course, 15 minus 7 is 8. And we have 0 left over here. So we say this little remainder right here is what goes right here. Now, these 2 answers, although they are both correct, this one would be accepted for credit because it is in simplest form. And recall that I cannot take a fractional answer on the DMCT especially unless it is in simplest form. Okay, moving on, we look at number 4 here. The only difference between number 2 and number 4 is this: we have whole numbers in front. Now, if we think about this in terms of logic here, you could think of this as like $11 and some change, and then we have $12 and some change. The thing is this: you can always pretty much deal with the whole numbers first. I would say, well, if you had 11 and some and 12 and some, you'd have at least how much? Let's just go ahead and deal with these whole numbers first. And like I said, adding 11 is pretty fun because you can just kick up these 2 digits one time. So it'd be 23. Here's the deal. We know we have at least 23 on the sum here. I say sum because this is an addition problem. The only thing left we have to deal with is what is 3/5 plus 1/2. Now here we go again, least common multiple between these two denominators. I say, well, what are the multiples of 5? 5, 10, 15, 20. Mentally we go through 2, 2, 4, 6, 8, 10. Here's the deal. The first one they have in common is 10. So what we'd like to do is transform these both into 10. And you're going to notice something kind of quirky on this one. We end up taking this one times 2 on top and bottom, which was this one's denominator. And we're going to end up taking this one times 5 on top and bottom, which was this one's denominator. So this whole kind of pattern always works this way. If you need to, you can always multiply each fraction by the other one's denominator. In this case, that does result in yielding the least common denominator. So rewriting this problem, we have 6/10 plus another 5/10. And here's what we notice. 6/10 plus 5/10, 11/10. So here's what we have. 23 and 11/10. And man, here I go again. Is this correct? It's correct. Is it in simplest form? Not quite. Now, 10 and 11 don't share any factors besides 1, because 11 is prime. 11 doesn't go into 10 evenly. But what I know is this: it's improper. I would ask, how many times does 10 go into 11? It goes in one whole time. So typically up here we would write one whole time. But remember, this is 23 and 11/10. And we can think of and as meaning plus. So 23 plus 11/10 is the same thing as 23 plus. In this case, it goes in one time with one of those tenths left over. So combining these two things, we yield a 24 and 1/10 sum. And that would be in simplest form. Lucky you, you're seeing this. Now, I'm not going to go all the way through number 7 with you, but I will get you started, and here's what you're going to notice. And they will pull this on you on the DMCT. I'm just warning you. And Mr. Johnson might in his tech class as well. But I look at this, I say 9 minus 3/4. You might say, well, hold on a second here. 9 doesn't have a fraction. Well, you know what? We could approach this in 2 different ways. One way to approach it is saying, hey, how could you turn any whole number into a fraction? Look, it's really simple. Can we just put it over 1? I mean, this really is 9 wholes. Okay, and in this case, well, we could make both of these into 4. Now, that's one way to approach it. The other way to think about this is, we could borrow from the 9. Interesting thing is 9, if you borrow from it, just like when you subtract, it becomes 8. What are we going to do with that other 1 whole? Here's what I would do with it. I would make it 8 and 4/4. I mean, come on. Logically, 8 and 4/4, that's the same as 9. And I actually like this approach a little bit better, because I can say, hey, 8 and 4/4 minus another 3/4. Hey, well, 4/4 minus 3/4, boom, I already got it in my head. I'm sure you do too. But you know what, I'm looking at this, and just if you do take this approach, I would suggest turning this into 4. And so taking both of these times 4, you rewrite the problem, you end up with 36/4 minus 3/4. Now, I'm not trying to steer you away from this method. It works every time and it's wonderful. The only thing is this: when you get done, I'm going to guarantee you, because you turned basically like $9 into 36/4 if you want to think about it in terms of money, you're going to have to simplify that again, which means turning an improper fraction into a mixed number. So, hope that helps you out. Good luck on the homework.